I'll wait for that.
Do you want me to listen for 10 minutes?
Pardon? I can watch the clock. Okay, sit down.
Come along.
Okay, so I'm going to tell you something about what happens when you put non-Newtonian and particularly shear banding materials, which has occupied my time, my interest for many years, and looking at some of the effects of boundaries and boundary conditions and surfaces on these. So first I wanted to say, some of you may be coming up to Leeds for the workshop that we have up in the north. For those who don't know where we are, now we're about there. And so Leeds is famous for some number of things. Beautiful countryside. It's a little bit farther north than Leeds, but it's not so far away. There's the university. We have a number of ales from Yorkshire, and so when you come, you have to make sure to partake in the local ales. Also famous for some other products. And actually one of the most famous things for me is that the Who's album Live at Leeds was recorded in the Leeds Student Union refectory. And for those who haven't been to the UK so much, there are these blue plaques around the country denoting famous events, such as people being beheaded and whatnot. And so one of these events is the Who's concert at the university. So, and if you come, you can go around the refectory and see all the concerts that went on back in the 70s, and anybody who's anybody came through. So I think that may happen today, but I have no clue who anybody is in modern music. Okay, so what I will do is first tell you just a little bit. I'll tell you a bit about, well, soft matter and how flow induces structure, and then give you some details into my view of shear banding, where flow can induce different phases. And so that is important for understanding what happens to some of these materials near surfaces. And I do need to go through some of the details of shear banding to get to that point. And what I want to say something about is, first, where there is no surface. So an example of a free surface instability induced by the normal stress effects of shear banding materials.
She should be beheaded, but that's good.
She has a door shut.
The boss job to go and do that.
Pardon? Yeah. And then what I will explore some of the possibilities of consequences of playing with the boundary conditions on the structural degrees of freedom, which hasn't really been addressed very much yet, and say a very few words about how wall slip, I'm going to kill myself, can play a role. But I won't say too much about that. I'd like to discuss that over the next coming weeks. Okay, so I think we all know what soft matter is. So a modulus, shear modulus is an energy density, and the typical energy scale available is kT, and the length scales that set the density are the length scale of the microstructure. So if you think about steel, which has a tiny microstructure, the modulus is huge. But for soft matter, where the structures can be quite large, nanometers or microns, just a simple back of the envelope estimate says that the stresses are very small, so it's very easy to perturb the structure, and that's why there's so many interesting things that can happen, because human stresses are able to easily deform what happens in these soft materials. And the important thing for understanding dynamics is that if you have large structures, they're inevitably going to be much slower than small molecule structures. Okay, so the relaxation times can be quite long, and it's very easy to apply shear rates that will exceed those relaxation times. And when that happens, you change the sort of steady state degree of molecular order, and then hence the mechanical response, and then one can get very interesting dynamics. So that's at a molecular or structural point of view. Okay, so it's an intimate relation between the stress, which induces something to flow at a given rate, the reorganization of the structure, and then depending on the time scale, the internal time scale of the reorganization of the structure, that can then feed back on the stress. And that gives rise to the phenomena that we're familiar with of shear thinning or shear thickening. In the shear thinning case, the prototypical example is an entangled polymer solution where the thinning occurs because you're progressively orienting the long molecules farther and farther, and then the apparent viscosity due to that goes down. And shear thickening can arise due to a number of effects, such as, for example, increasing intermolecular associations because you rip them apart by flow and then they find others rather than themselves, or in dense suspensions creating force chains and clusters of larger sizes. Okay, so these are some examples of materials where the flow is induced the structure to change the state. So this is a colloidal suspension, and we're looking at the edge-on view of a cylinder where one sees a nice shiny band, which is essentially very, very large domains of well-ordered crystals of the colloids, and then you get disordered polycrystalline state. This is a so-called onion lamellar surfactant phase where the matrix is a disordered lamellar phase, and the spheres are where the lamellae have ordered themselves due to flow to roll up into spherical objects microns in size. There was an interesting set of experiments done 10 or 15 years ago by the Montpellier group of a colloidal copolymer micelles, where they could actually see 3 versions of structure appearing in the layers of these micelles under flow: a disordered polycrystalline structure, and then 2 variants of layer sliding, where the layer normal was pointing in different directions. So you can get elaborate structure occurring depending on how the stress interacts with the molecular and mesoscale degrees of freedom. And the example in the middle is a rod-like virus suspension. I think this is the FD virus from the Jülich group. And we're looking again edge-on in a Couette device. And in fact, these dark and light bands, they look like they have different birefringence, and in fact they do. And in fact, what's happening here is they've induced some sort of Taylor roll-like structure of the liquid crystalline material with a substructure, which is, you can't see it very well on the screen, but the substructure is little tactoids of pneumatic in a weakly isotropic phase or vice versa, and the whole thing is spinning around. So there's some very interesting dynamics here, which I'm not sure has really been worked out. Okay. So the object that I will focus on is a constitutive curve which has 2 steady states hanging around and a shear thinning case. So this is a cartoon of stress as a function of shear rate, and the example where this shows up most readily is in worm-like micelles, shampoo, where if you can exceed the relaxation time for stress to relax, which is a combination of the reptation, that is the snaking of these micelles through the entangled mess, together with breakage. The combination of those leads to a relaxation time, which can be of order a second, very easy to exceed. When one exceeds that, the stress goes to a maximum, and then at some point the stress goes up again because there is a solvent viscosity. And so the net result is a non-monotonic stress versus shear rate relation, which has very interesting dynamics that can occur. So, and if one looks at this in steady state, these materials indeed give rise to shear banding. And this is an example looking down from above, where the material has actually phase separated into a high shear rate phase, which would be the weakly birefringent, the strongly birefringent phase up here in this upper branch, and a low shear rate phase on the lower branch. And if you control the stress, the material jumps at a given stress. You can ask a question? No.
Just reminds me of the Van der Waals phase, the Van der Waals phase diagram.
Yeah, very much.
It's like that.
We'll come to that in just a second. And if you were to instead control the shear rate, then exactly with liquid vapor, where if you compress it and you change the volume, you gradually change the volume from one from gas to liquid at a given pressure. Here, if you change the shear rate, you convert from low shear rate to high shear rate material along a given well-defined stress. So yeah, it's very much like van der Waals. And so then the question is, how do you understand it? And how do you do the analog of the Maxwell construction, which you would do for van der Waals? Because if it's out of equilibrium, you can't use a Maxwell construction. There isn't free energy, and there's no chemical potential that you can use to construct the Gibbs-Duhem relation to give you equality of the equal areas. So you have to work from the dynamics, and the simplified dynamics would be, say, a total stress, which can be partitioned into a viscous stress associated with the viscosity and the shear rate, and a microstructural degree of freedom, sigma p for polymer, for example. And this object has its own dynamics, and this dynamics is nonlinear, and as a result, in steady state, the nonlinear solutions to that for a given shear rate, combined with the viscosity, give you this sort of non-monotonic relation. And that shows up from a variety of different models, such as entangled polymers, liquid crystalline models, or like micelle models. Okay. So in steady state, which is what these experiments show, the left side is equal to 0, and then we have to maintain stress balance, force balance, which means you have to have the two states that coexist have to have the same stress, and then of course the question is, what's the stress? Okay. So if you don't want to invent anything, such as a free energy or a dissipative function, what you can do is say, well, a real interface between two shear rates and two materials should have a finite width, which is determined by the microstructure in the material. So that means the dynamics, and in fact the stress constitutive relation, should care about internal gradients. And so there it is. And if we try to solve for the steady state conditions of an interface at a particular imposed stress, what do you find? Well, you cross this off, and then the full equation set in this simple case would be a second order differential equation, nonlinear differential equation, and we have boundary conditions at either side.
Okay, so could you talk about the physical meaning of the D?
Do you want me to?
I'm doing both, that's all.
You are. Okay, so that has to do with whatever your substructure is, and if you have entangled polymers, there can be contributions from the weak but nonetheless finite bending elasticity of the polymers. So that means that length scale will be of order of persistence length of the polymer, which can be quite small. For entangled polymers, in fact, the constitutive relations for entangled polymers are only valid to a length scale which goes down to the tube diameter. And so there will be a length scale determined by the tube diameter, below which there's more information that isn't in the bulk constitutive relations. If you have polymer solutions, there will also be a concentration effect here as well.
But you also need a time.
And you need a time. And you need a time. And so the time comes about because if we think about the fact that this is hiding, that this is, you can think of this together as a internal degree of freedom, which in the absence of any flow might be relaxing according to gradient dynamics with some relaxation of free energy to equilibrium. And then if the contributions to the square gradient terms arise from the free energy, which is something plus gradient terms of the microstructure, then those gradient terms will naturally emerge in here, and then the time scale will be set by the overall gradient dynamics in the absence of the flow, and this so-called diffusion constant will be a combination of that time scale and whatever constant is in front of the square gradient terms. It's not to say that's the only source of gradient terms, but this is an example. You could also get, if you were to take hydrodynamic interactions seriously and then do some sort of gradient expansion in the hydrodynamic interactions, there will be something else that comes from that. So, if in steady state this is a set of second order differential equations in space, the typical shear banding solution you might imagine is that when the interface is far from the walls, the shear rate and in fact the polymer stress has to be the values that are on the homogeneous constitutive curve, so that sets two boundary conditions. And if we go far from it, we would also assume that if we go far enough away from it, there's no gradient. So that's two more boundary conditions, so that's 4. Okay? But it's a second order differential equation, so there's no solution. So generally, there isn't a solution which connects the two branches. If you control the stress at which you choose these solutions, there can be a particular value of the total stress at which these 4 boundary conditions become two sets of degenerate boundary conditions. And at that point, there's an isolated solution where you get a kink profile. So mathematically, that's a heteroclinic connection between these two fixed points, or an inhomogeneous profile. And if one has just a very simple toy model with a single set of gradient terms, the value of the stress at which the two states coexist is independent of the diffusion term, because that just sets the length scale of the interface. But if the system size is much larger than the interfacial width, then the magnitude of it drops out of the system. So it's a singular perturbation to the whole equation set, and so you just need to have diffusion terms there to be able to get this selection. Okay. And these gradient terms, of course, will control the growth of spatial structure in the material, such as how fast will an interface propagate between two phases. If you were to do the analog of spinodal decomposition by doing a rapid strain rate jump in the middle, how does that subsequent evolution evolve? And what about interfacial instabilities which can occur during the shear bending case?
So could you maybe try and help with a single PDE description here? So if I substitute gamma dot using the left-hand side,
So we have 0 is equal to some function. So sigma e gamma dot.
No, I was actually looking for the full dynamics. So the keep the derivative with respect to t of sigma t.
Okay.
And what is the dynamic evolution equation?
Aside from that.
Well, I guess it's not. I just don't see it as a closed system right now. I'm a bit puzzled by what sigma tot is.
So sigma tot. Okay, so in some little region of space, that region of space has a shear rate associated with it, and there's an average value of the internal, the microstructural stress. And so if you say what's the total stress exerted in that system, so you pick a little wall cube, and that's all the stress going across that interface, it has contributions from the polymeric stress and the viscous stress.
But in the second equation, you're thinking of gamma dot as just a parameter.
In the second equation, I'm thinking of gamma dot as being a parameter.
It is a dynamical variable,
Yeah.
but the problem you're solving is the steady state flow.
But you can solve the full dynamics.
That's what I was trying to do.
Yeah. And so, so if you solve the full dynamics and you do the zero Reynolds number case, which you might want to take, then this equation, the left-hand side has to be a constant in space for simple shear flow, because this is solving div sigma is equal to 0. Okay, which means that the total shear stress has to be uniform.
But a priori, you don't know what that is.
You don't know what it is. That's right. Yeah. So what you
For
do?
the initial value problem.
Yeah.
Does the initial condition set it?
So the initial condition that one applies is an initial condition of the local value of the shear of either gamma dot or sigma p, and because the whole thing has to be uniform in space, there's a constraint between the dependence of these in space, which must demand this constraint. And then it's a little bit tricky, but you can write it down. And then in fact, what you find is you can express gamma dot. So gamma dot y will be the total stress, which is independent of y, minus the local microstructure variable, which depends on y. And so when you solve this dynamics, you replace gamma dot as a function of y.
Why doesn't the microstructure add forces to the
Pardon?
Why doesn't the microstructure add forces to the total?
The
In other
forces.
words, you're doing Stokes
Yeah.
keeping flow.
Yeah.
where you
So this is
exercise your-
these are the forces with the microstructure.
You're insisting that you're having a steady shear.
I'm insisting.
so-
I'm insisting. No, I'm insisting. You can make this tensorially accurate, if you like.
No, I'm not worried about that.
Okay.
I'm worried about the equilibrium. So you want your equilibrium to be a straight shear time independent. Gamma dot constant.
No, I don't.
Well, that's not what's going to happen.
No. All I'm demanding is I'm demanding that.
So that's okay. So that's what I'm asking you. So
That doesn't mean gamma dot constant. This means a uniform total stress.
right. But if I were to write down, okay, so what I'm familiar with is an equation for the fluid that's driven by divergence by that thing.
Yeah.
Right. So you are taking no flow.
No, I'm not taking no
He's
flow.
taking no inertia.
I'm taking no
No
inertia.
inertia, I understand, but
Well,
that's
there's no inertia, do sigma equals 0, that's it.
so that contains also the viscous thing. Right.
Yeah.
Okay. Now
Yeah.
that's notation. All right. Okay.
Yeah.
All right.
So no, that thing will be
All right. All right.
So,
Right.
it's already done.
Notational stuff.
plus eta times some. Do it properly. Some.
All right. All right.
Thank you.
Sorry. Okay.
That's okay.
So,
But that's exactly what I was asking.
yeah, so last thing, if you take this again to the gamma dot, the replacement, if you integrate that in y,
Exactly.
then you get a non-local
Yeah.
representation for sigma total.
Yeah. So sigma tot is exactly that. You can write it as an integral average over y
Yeah.
of whatever it is, gamma dot
Plus,
y
Yeah.
plus sigma.
plus sigma p. Yeah. Yeah. And so then you can then replace it when it shows up in there by something that involves the average over the whole system of gamma dot. So this whole set then reduces that to an integral differential equation
And
for
so-
gamma dot
So
or for
sigma,
sigma p.
so this sigma total is a function of time, but it relaxes to a final state. It's constant,
Mhm.
but it's a constant
Precisely.
function of time.
Yeah.
Exactly.
Okay.
Yeah. So it's a uniform constant which depends on time, and it'll sort of jump. If you were to jump it to an imposed shear rate by the boundary, it'll jump up and it'll rattle around as the whole thing becomes homogeneous and then settles down.
So these stationary solutions you're looking for are the critical points for that dynamics.
Yeah, in some sense.
I mean, so I guess this is really for shear flows.
Yeah, the construction I'm talking about is for shear flow.
So what about when you have extensional flows?
So extensional flows are, okay, let me,
That's another tool.
yeah, well, I will perturbatively address that in about a slide and a half. Okay, but I'm not going to get very far.
Could be several hours time.
Pardon?
Several hours time.
Yeah, no, it's no choice because it's on the next slide. Okay, so this gives you a way to construct the dynamics. Okay, and so there's a single stress determined by essentially by the equation set at which things will coexist. Okay. However, so this is getting perturbatively towards Tan's question. So most real devices have an inhomogeneous stress of one sort or another. You don't have infinite plates that you can shear for a long time. You might have a Couette device which has a stress that decreases with radius. And so if one looks at the constitutive curve, then if you have a profile that extends between low and high shear rate states, then in fact what that profile is doing is it's moving in space from high to low stress, so from high on the inner cylinder to low stress, and it's coming across like so. And so you're expanding a portion of the constitutive curve. And in fact, if you're able to access the local velocity profile by measuring it using optical measurements or otherwise, you can actually map out the constitutive curve by moving this along enough. Okay. So you can map out this bit here, you can map out this bit here. And as long as there's a separation of scales between the length scale at which the stress decreases and the width of the interface, then the selected stress will still be the selected stress from the flat calculation. So as long as you get that separation of scales, which is usually the case, then you can treat it as if the interface is moves to the stress at which the interface is stationary. That satisfies the first condition that we wrote down. Okay. It also means that okay, if you were to say rotate the inner cylinder at some average shear rate, the interface is sitting somewhere, and now you want to do what you would do with flat plates. Move it a bit faster to move the interface out. You have to convert more of the material to the high shear rate phase. If you rotate it faster, if the interface moves out, if the torque is the same, that you feel the torque at the wall is the same, then if it moves out, it moves to a position of a lower shear stress. But it can't be stationary at that point, because it can only be stationary at the selected shear stress. So you've got to also increase the torque so that at the interface has moved out, the stress at that point has come up a little bit to account for the stress gradient. And so that means in a real device, you shouldn't see a dead flat stress plateau. You should see a curved stress plateau, which reflects the inhomogeneous shear rate in your device. So most plots are done on a log-log scale. If you do them on a linear scale, you in fact invariably do see some curvature. So these is experiments from the group in Bordeaux at the time, where they measured the stress as a function of shear rate in a Colette device, and the dots are what they found from the torque on the rheometer, and you can see it's not a plateau, it's a slightly increasing plateau. Okay. But what they could do is they could visualize where the interface was, and therefore find what the stress was at that interface as it moved across. Okay. And this is a slightly complicated figure, which I can't even remember what's on the axes, but basically what they were able to show is that the stress at the interface stays the same stress as it moves across, even though the overall torque is increasing. So it does stay at particular stress, which is characteristic of the material as it moves across.
Peter, these bands are not along the cylinder, right? They are between the two plates. So this is then for low shear rates, and then you get this becomes unstable if you go to higher ones.
And so this case is where the interface between the bands is like that.
But the initial picture you showed of the crystal and the random phase and the colloidal suspension.
Oh yeah, that had a structure in the other
So
direction.
this would come if the speed goes higher, or
That was a different material,
Different material.
totally different material. And you can have materials where the constitutive relation looks like that, or the constitutive relation looks like that. And in these cases, you can now get material that has the same shear rates but different stresses, like that. And that would correspond to something which is structured like that. I propose not to talk anymore about those. So obviously normal stresses play a bigger role in that particular case. Okay, why does this have anything to do with boundary issues? Well, if we're going to look at things in boundaries, we've got to worry about the boundary conditions. And the boundary conditions obviously play a role in understanding the selection. And I've assumed the simplest boundary condition in doing this, and we've done a lot of calculations with these kinds of materials where we've just assumed that we have zero gradient in the microstructure at the boundaries. And so, but what do people find? Well, all sorts of things happen in reality. Up here is an example of cone and plate rheometry on worm-like micelles. And the shear band in this particular case is in the middle of the system rather than on the boundaries. And there is some indication that this could be a thin band which is fluctuating quite a bit, and that fluctuations of the band causes it to smear out. But there, if you look in Callahan's measurements on these, you can see a variety of things, and the bands are not always, in fact, they fairly rarely are on one, either on the cone or on the plate. It's often displaced in the middle. Okay. This is an example of flow curves from actually a tri-block copolymer micelle, so a worm-like micelle made of copolymers. Shear stress as a function of shear rate. There's a Newtonian region. There's a region of wall slip, which is not a shear banding state. And then there's a region where the wall slip goes away, and you end up with actually a three-band state, similar to what I showed you, similar to this one. Okay. And then above a given shear rate, it becomes unstable. So there's some relation in this particular system between how much it slips and whether it bands or not, kind of thing. And this is an example of the stress as a function of shear rate for worm-like micelles confined to small microchannels of 100 or 200 microns, I believe. Yeah, 100 to 200 microns. And the black curve is the relation between stress and shear rate extracted by measuring on a rheometer for these materials. And the symbols are the relation between the wall stress, which they know because they can work that out from the flow of the material through it, and also visualizing the local shear rate. So they have a relation between the wall stress and the shear rate at the wall. And near the wall, you can see that the material doesn't follow at all the bulk constitutive relation in a variety of cases. So evidently in this case, even though the width is 200 microns or so, which is often thought to be larger, much larger than the length scale set by this diffusion constant, it's having quite a large effect on the apparent rheology and hence on the flow of the material. So those are some of the kinds of things that one might try to understand. Here are examples where this is an example of a shear thickening worm-like micelle, and this comes from actually Amy Shen's group a couple years ago, where they extruded a worm-like micelle through a bead pack. Okay, and after squirting it through, out came what they call, well, this is it coming out, and here it is coming in again, a very thick gel, shear thickened material, which is not a material they could produce in a rheometer, and it's stable for quite a long time. And I'm not sure they've actually worked out what the structure is. Maybe people are more familiar with their more recent stuff than I am. And it presumably has to do with the interactions at very confined geometries and different flow fields with the surfaces. And so the interaction of the material with the surface can induce new structures which aren't structures you can get out of bulk flows. Okay. So what are some of the things that we could try to look at? The effect of confinement when the length scale gets small compared to interfacial widths or other intrinsic length scales. Something about the boundary conditions and how the effects of boundary conditions can interplay with the shear banding. The boundaries can be compliant in many ways. So one idea is, of course, wall slip, which can occur, but there are lots of boundaries where they're not just boundaries, but they're dynamical degrees of freedom living on those boundaries. You can have semi-permeable membranes where the degree of permeation depends on the local stress. You can have polymers adhered to the interface whose dynamical state depends on what's going on. And then, of course, free surfaces are the sort of ultimate boundary, ultimately compliant boundary. Okay, so let me say a little bit about free surfaces that we've looked at. Okay, so these are measurements on an entangled polymer solution. And the top view is sort of low shear rate, looking between a plate at the bottom of the cone at the top. Okay, and then they've increased the shear rate, and after some time you can see it's sort of submerged outside, and then down here there's nothing left. It's sort of ejected. Okay, so some of you may recognize that this is like the so-called phenomena of melt fracture. Okay, and this is the stress is a function of shear rate for this material as measured in the rheometer. Okay, so it starts to shear thin, and then it ejects at some point, and the measurement gives you a decrease, either a decrease in the stress and also an increase in the apparent shear rate because it's been ejected. The onset of where it's ejected depends on the width, the thickness of the cone and plate, actually the cone angle. Okay. And so I can't remember which one is which. I think in the smaller one, which I think is 2.5 for some reason, it delays the onset much more dramatically. Okay. And so an explanation for the instability at the free surface is that it's a combination of the normal stress of the material, second normal stress, if you apply a shear like that. The first normal stress has to do with pushing the plates apart, and the second normal stress has to do with the stress coming out in the vertical direction, in the vorticity direction. Okay, so it's a combination of the second normal stress, which is going to have to be balanced by the deformation of the surface, which is related to the surface tension and something to do with the width of the interface. Okay. Now, this has been looked at for quite a number of years in just thinking about a homogeneous polymer melt or non-Newtonian material. In fact, this material is accused of being a shear banding material, and there is some evidence that it is. So a question is it possible that something to do with the interplay between shear banding and the second normal stress effects can lead to the ejection and the instability at the interface? Okay. And so my students looked at this in a very phenomenological way. So we said, let's imagine we have a material which is capable of shear banding, and it is shear banding, so we've applied an average shear rate so it's shear banded. Okay. And this would be the side view of two plates that are being sheared. In the top, this would be the meniscus sort of bulging out. Okay. And we have two different materials with two different second normal stresses, which are stresses acting up. In the limit of small deformation, then the stress balance condition on both of these is that the second normal stress has to balance with the surface tension and the radiated curvature of the two bits of the meniscus. Okay. And we need to say, well, what's happening at the contact angle? We say that the contact angle is fixed by the chemistry. You could also do a case where the contact angle isn't allowed to equilibrate because it takes some time, and that's another thing that can be worried about. We haven't worried about that too much, but you could imagine that it's pinned, and so the boundary conditions are in fact that one of the interfaces or the other one remains pinned, or you can invent a pinning constitutive relation. Okay. We haven't worried about that. We've said let's consider that there's a fixed contact angle that remains. Okay. So there's a control parameter, which is essentially the balance between these two. So it's the normal stress, the length scale of the system, L is the gap size, and the surface tension And because the normal stress and the sort of shear stress roughly have the same sort of order of magnitude, you might say that it's in fact the second normal stress relative to the shear stress and the shear stress. So essentially, a balance between how non-Newtonian it is and the surface tension, similar to the Keen-Top case. Okay? And so if you forget about the length scale of the system, there's a capillary length, if you want to call it an elastocapillary length, which balances surface tension against the modulus, and that length can control some of the things that we shall see.
Are you going to argue, Peter, that
Not gonna argue.
edge failure?
Pardon?
Are you going to say that that edge failure actually has to do with shear bending? So far, you haven't talked about shear bending.
I'm going to say that it could be due to shear bending. Okay,
Yes.
so in this particular case, I have a shear. This is a shear banded case, right? So actually, let me be a little more careful. So the inner side,
You've drawn a shear bend.
yeah, the inner bit here is on the low shear rate branch, and the outer bit is on the high shear rate branch.
So there's different curvatures on that curve at the top.
Yeah.
I
So
think.
this is not supposed to be a semicircle. In fact, it's not.
So this kind of failure, isn't that quite common with polymer melts in solutions?
Yeah.
Wouldn't there be sort of a generic explanation for that without evoking exotic?
Yeah. No, there is that, and the Keen-Top one is an example of that. So if you just have a homogeneous second normal stress, then it can eject. What I'm saying is that if it is a shear banding material, then you can get an ejection, because although you basically want to ask when does one of the bands start to fail. So
Okay.
it's related to the garden variety explanation.
So you fix the contact angle. You also said you could pin things. You need something. Do you need to know something about the contact angle? Because it seems to me that in many cases you'll have a slot with a corner, and then the contact angle can just
Can
be
do.
anything at the
Yeah.
corner. And I wondered if that problem is well posed, or whether that would require some additional physics to be inserted.
Yeah, I don't know whether that's well posed. So we asked Sandra LaRouche to try to look at this, so she's been able to image the interface and watch it go across. And actually, she's purposely done it so that it's not near a corner.
Okay.
Okay. So what you typically will find is that one side,
You underfill the thing.
yeah, you underfill the thing, and then it'll sort of scoot up one side. But of course, when it gets to the top, then there's something interesting happening. But so. So these are two examples of, so actually let me just say, see, so if you do the very simple calculation of saying, well, let's just do mechanical balance for the shape of the meniscus. And so we maintain it's got to have continuity and also continuity of the slope at that point, and it's got to do mechanical force balance. Haven't done anything about secondary flows inside, which is a whole other set of problems to look at. So that this is modulo, the true dynamic calculation, which would involve calculating the flow field in there, which is what Keen-Top and Tanner did a little bit of. So in this case, these are two different contact angles, and what I'm increasing as you come down here is essentially the size of one of the shear bands, and these are the typical shapes of the meniscus that you can calculate. And then at some point, one can find a case where the meniscus goes, basically it can overhang, and you can't find a solution, and in fact there'll be a solution which overhangs with itself at some point.
I'm not quite reading these pictures.
Okay.
What's the grey shading mean?
So the gray shading just means light gray is
Band 1.
band 1,
two.
and dark gray is band 2.
Okay.
Okay, so here I don't have any of band 2, and then I'm increasing the amount of band 2.
But I should be viewing these as the meniscus shape between parallel plates which are vertical.
Yeah, you can think of the left-hand side as being, actually think of the right-hand side, either one, as being the cylinder, the inner cylinder, and the other one being the outer cylinder. and this is the top of the couette. Okay, so this would be the deformation of the meniscus at the top. Okay? And then, depending on the contact angle, you find that if you try to match just the simple mechanical boundary condition of the interface, you find a place where it starts to overhang with itself, and you can't find a solution. And that would correspond to you come across the stress plateau to some point, and then in here, you can't make a solution this way. And so that would say you would see shear banding up to some point, and then it ejects. And in fact, you can play around if you play with the contact angle, and so this is the width of one of the shear bands. There's a region where one finds an integral meniscus all the way across, so it'll bulge and do things as the shear band moves across, and then there's a region where it just fractures at some point, or you can't find a mechanically stable interface at some window, and this is where it would fall apart.
But I mean, that just, I mean, you could imagine that just because you need to put more physics. You could put in, it doesn't have to be ejection. It could be, for example, you'd have high order gradients or something.
Yeah. So this is just saying this simple description breaks down, and one needs something else. And we also haven't included the honest secondary flow calculation, which needs to be done. So, and that'll probably destabilize it even farther rather than stabilize it. But there are others here who can probably say more about that. So is an artist's rendition of what might happen. Okay, so it's all controlled by this single parameter called A, which is essentially balancing the second normal stress with the surface tension and the width of your gap. Okay, and so you can find a region where if A is sufficiently large, let's see what A is. So when the second normal stress is big, or the surface tension is small, then your control parameter is large. Okay. So when it's sufficiently large, then it's unstable at some point. Okay. Right. So there you can find a place where it's unstable. If it's really large and it doesn't get very far across the plateau, so you can think about the x-axis is moving across the stress plateau. You don't need to get very far across the stress plateau before it's unstable. So everything between this line and that line is unstable for A is equal to minus 10. Okay? And so you find different types of behavior. Okay, so now what are the shear banding materials that we look at typically? Worm-like micelles are one, and entangled polymers are another. Okay, and if you just do back of the envelope estimates of the numbers, polymer solutions or entangled polymers would have a value of A which is quite large, 10 to 100, whereas worm-like micelles can be significantly smaller. Okay, and so the first we'd actually do a comparison with worm-like micelles. So you can look around in the literature.
So where did those numbers come from?
So those numbers came from
A involves knowing the difference of
the difference in the second
normal stress between the two phases, so there's not much data on that, right?
There's not much data on that.
But there may be some theory.
So what we do is we took a few different constitutive relations, fit those to the available shear data, and took the second normal stress that comes out of the calculation. Then we did it for 3 or 4 different models, and they're not that different from each other.
But why are those two things so different from each other?
Polymers and worm-like micelles?
In this particular respect?
Yeah, it's because the entanglable polymers have a much higher viscosity, basically. So you're looking at
So you might get down to that kind of value for polymers if you had some absurdly ultra semi-dilute limit or something.
Yeah. Or if there was some reason, polyelectrolyte or whatever, that the viscosity could go down. That's why I said that if you normalize the second normal stress by the shear modulus, and
but it's got more to do with concentration than what kind of dynamics.
Yeah, that's right. Yeah, that's right. Okay, so if you look around the literature, people don't say much about plateaus that end, and you have to sort of look in the details about how they did the experiments, and you find that there's about 3 in the literature where they fessed up to the fact that are ejected from the rheometer. Okay? And so if you look at the ones where it's been ejected from the rheometer, those are where this parameter is towards the more unstable end. Of course, it's very, very crude. We don't know what the actual values are. And in the case where it seems stable as you move all the way across, the parameter is more towards the stable region. Okay. So does that answer your question? That maybe, I mean, I think it is the Tanner-Keentop argument, but it's saying that if you have shear bending material, one reason that it ejects is that one of the bands combined with the mechanical balance between those.
In the artist's rendering, there's no, in your solution, there's no shoulder, right? You have the shoulder actually having the traffic line moved around the corner, the top figure.
Oh, the top one?
Yeah, that's not what you have, right?
No, probably not. That's why I said this is pure. These figures are pure fantasy. So I should remark that. Actually, not completely sure, because I have a video that I can show you, which from Sandra LaRouge, who has tried to image the meniscus coming out, and it does sort of do.
In reality, perhaps, but in your solution, that's not.
No, the solution can't
You have
address
to
that at all.
introduce the anchoring, sorry,
Yeah.
the singularity, the indeterminacy there,
Yeah.
and
Yeah,
you know.
so that's not in it at all.
Yeah, right.
And in the entangled polymer solutions, okay, the people looking at these most recently, actually they're trying to disentangle whether the material's shear bend or not. So that was sort of the argument this is in the literature. This is polybutadiene, this is polyacetylbutylene, I think is the name. Okay, and they have different moduli, different characteristic moduli by about an order of magnitude. And this parameter that one finds, if we do our best to try to estimate, depending on the geometry that's been done, the case where there is a case that's stable most of the way across, for where this parameter seems to be in the more stable regime, whereas the other ones can eject fairly rapidly as you get across the stress plateau. So that's what we think what may be happening here, is it starts to bend, and then the high shear rate band gives you a big difference in second normal stresses between those two, and it's amplified by essentially the high shear modulus of the material, and that causes it, well, at least that's not the dynamical cause, but that set of parameters leads it into the region where you can't get continuity. Okay. You can play with slightly more exotic things. We looked at the possibility of 3 bands. I'm thinking about Paul Callahan's data, and there's a whole set of interesting things that one can imagine coming up with. All right, so I've got to 3, so maybe I should stop. Because someone else is talking at 3?
Yes.
Okay, so I'll stop, and I've got another talk I can give some other time.
Can you describe what this bottom right picture is more precisely?
Sure, yeah. So at the bottom is the flat plate, and there's a cone. Okay, are you familiar with cone plate geometry?
No.
Yeah, so that means that the shear rate is pretty homogeneous inside. Okay, and then they've used NMR velocimetry to find the velocity profile inside.
Could you draw a diagram to show the geometry?
Yeah. And the material is placed in here, and this thing is rotating. Okay, so what they've done is they've mapped out the velocity in here. So here the velocity is going, say, into the board, and here the velocity is coming out of the board. Okay, and there's a no slip boundary condition here, and this is rotating, so in fact what's happening is at some point, well, it's going in like that. So there's a shear rate which is homogeneous as you move across. Okay. And so in fact what they find is, say white for example is coming out at you, black is going away, And then you've got a region in the middle, which, in fact, what they've done, they've differentiated it, the velocity map, to get a velocity gradient map. Okay, so you've got a more or less the same gray velocity gradient on either side, and then in the middle, you've got a high velocity gradient, either going towards you or away from you, and that would correspond to the shear bend.
So the shading is not the velocity, it's a velocity gradient.
It's a velocity gradient.
And that correlation you're seeing, that's just a
That's
feature of the...
it's a feature of the what they've done. In fact, it's the cone angle is this is not the cone angle.
No.
What they've done is they've blown it up so you can see it. And so the cone angle is a degree or two.
Aha.
And so they've increased the vertical axis and stretched it so you can actually see what's going on.
Didn't they use inertia to explain some of edge failure in polymer solutions?
Who?
I don't know. That's just the impression. They. So
They.
I was wondering, okay, so if you
They probably did, yeah.
if you do the secondary flow calculation, I wonder if that actually comes before or after the N2 failure, because N2 is quite small anyway.
It's a very good question.
N2 is
There
very
is.
subtle.
Pardon?
N2 is very small.
Yeah, N2 is very small. Yeah.
How well do we know that?
I don't know that we know that actually. You mean, do we know what N2?
Yeah, experimentally. I mean, there's only a few people measure it at all.
Yeah.
It's true that the polymer theories say it's more.
Well, there are data.
There's some, I know.
Yeah, there is something
It's,
there.
yeah.
There's some.
But it doesn't have to, I mean, the point is that it's not being compared with N1. It's just being compared directly with other parameters in your...
So in this case, it's basically the relation between N2 and G and the modulus. So that's a dimensionless quantity. And then there's an amplification factor, which has to do with the overall modulus of it. But there has been some back and forth, I think, about whether it's inertial or not.
What I'm asking doesn't really have to do with your study. So
No, but it's interesting. If you try to go through the literature, it's sort of...
I'm just thinking of a real solution and which happens first.
Mhm.
A mathematical question. So the
We are in mathematics.
so the stress relaxation you were describing in the beginning is to the Maxwell line.
Well, if you want to call it a Maxwell line.
If you want to call it that, so effectively a Maxwell line. When you introduce this coupled system where you have a capillarity
Mhm.
coupled to the flow, you expect the same stress state. Because there's an energetic contribution now coming from the interface. I was wondering whether that...
I don't know. It would presumably there'd be things happening up near the top, but if that's big compared to everything else, you know, if you got a really tall one.
Oh yeah, sure, but I mean, not using separation of energy scales,
Yeah.
but if it was competitive energetically,
Mhm.
would it influence the final equilibrium state? Because I was wondering how you're controlling, because you're basically setting.
Yeah. So in this case, we're setting it. We're saying we've got an overall partition of bands, which is set by what's happening down in the bulk.
Yeah.
And of course, as you get near the surface, things can happen. And the one experiment I've seen shows that something happens as it gets near the surface. And in fact, it may be that, okay, I should let, who's speaking next? Okay, let me get off. That's not fair.